Hello, statisticians. Mr. Youngsaver here from Skew the Script. Following the COVID-19 pandemic, many colleges across the United States decided to go test optional for their admissions, meaning they no longer require submission of the SAT or the ACT to apply to their school. Now, many of those colleges have decided to keep that policy post-pandemic, as it's just so much more convenient not to have to evaluate all those tests. But some colleges, and more colleges year after year, are deciding to go back to requiring these tests. And our question is, why? We're going to explore that using regression and measures of strength. Let's skew it. Today's lesson's on measures of strength. This is lesson 3.3, day 2 in our course sequence. So the big tests we discussed last time were the SAT and the ACT. They used to be always required to apply to schools as a high school student. But then in 2020, the COVID-19 pandemic happened. And during that year, testing centers across the country and across the world were shut down due to the virus. So colleges, by and large, canceled their testing requirements. And as the pandemic waned, students in colleges realized that they could save money, save time, have less stress if they decided to make these tests still optional. So some colleges have vowed never go back to requiring the SAT or the ACT. Instead, they just said, we're going to be looking at GPA as our only measure of your academic success. However, other colleges and more colleges every year since the pandemic has waned are requiring the SAT and the ACT. Some of those colleges are listed here. So that's our key analysis for today. Why would colleges choose to require the SAT and the ACT once again? If you'd like to follow along, you can print up our guided notes at this URL. One of the world's largest school systems is the University of California University System. And in 2020, they released a study of standardized tests and admissions. This is a very rare event because it's rare for the public to get a good look at admissions data for such a large school system. That kind of data is normally kept private. Now, one key admissions office goal is to predict which applicants to the school will perform well in their college classes, i.e., what is the student's academic preparation. And traditional indicators of this are high school GPA and your SAT or ACT score. So we have 1,000 simulated students from the UC system, and we have their high school GPA, which is unweighted, so maximum of 4.0, their SAT score, which was out of 2,400 points at the time, a composite of their high school GPA and SAT score, which is basically the percent of points you could have earned in your GPA out of 4.0, and the percent of points you could have earned on your SAT out of 2,400 combined. So it's evenly weighting how you did GPA-wise, SAT-wise together out of 100%. And then the final variable we're going to look at today is the first year college GPA of all these applicants who were admitted. That's the response variable, the outcome. So first, let's take a look at their high school GPA and their first year college GPA. So we can see here that it seems like the higher the applicant's high school GPA, it tends to be a higher first year college GPA once again to college. So how can we make that prediction a bit more formal? Well, we can fit a least squares regression line model to it. And we do see that there is a positive trend here. So if I wanted to make a prediction as an admissions officer for a student who has a high school GPA of 3.5, I can go ahead and use this with my model. So 3.5 is the X value. That's the student's high school GPA. I can drag that up to my least squares regression line, plug it in to get the Y value. And the predicted Y value is 3.1. That means that we predict their college GPA will be about 3.1 points. There's one problem though, which is there's a lot of variation here. Yes, we say on average, we would predict that this high school applicant with a GPA like this would get about a 3.1 college GPA, but a lot of individuals got GPAs that were a lot higher than 3.1 or a lot lower. You see a lot of vertical variation, a lot of high residuals around this point. So how can we improve on that? Can we find a better predictor of college GPA than someone's high school GPA? Well, we can try out a couple things. One, we can try out their SAT score. So here's the relationship between students' SAT scores in this data set and their first year college GPA. A final variable we can try is a composite of the high school GPA and the SAT. So doing that averaging out of 100%, giving equal weight to GPA and SAT points, is this composite measure a good indicator, a good predictor of your first year college GPA? So we have these three candidates on the table. I want you in the next screen to pause the video and think about which one of these looks like, just visually looks like the best predictor, the strongest predictor of college students' GPAs. So pause the video on the next screen. All right, Now you've thought about that, we also might think there has to be a way to precisely measure which of these is best, which of these is the strongest predictor, rather than just visually looking at how can we precisely measure that? Well, one precise way to define that is which model has the least error, which model has the smallest residuals when you're using that regression line to predict the data points. So in order to evaluate that, we have to use something called the standard deviation of residuals. So standard deviation of residuals is defined as the typical error between data points and the least squares regression line, i.e. the typical residual length in our model. So if we look at two different data sets, data set A and data set B, we can see here that data set A is a very strong relationship and data set B is a weaker relationship. Data set A, the values are very close to the least squares regression line. We'll have very good, accurate predictions with that model compared to B, where there'll be a little bit more error if we make predictions with this model. So exactly how much stronger is that relationship? How can we quantify that? Well, we can go ahead and plot the residuals. And as you might expect, the residuals in A are a lot smaller than the residuals in B. And we can measure this thing called S, the standard deviation of residuals, the typical residual length for each of these plots. The S value might look like something like this for A. The S value might look something like that for B. These are the typical lengths of those residuals in either plot. So the stronger the correlation, the smaller the standard deviation of the residuals, the smaller the typical length of the residuals. The weaker the correlation, that means there's more error, the larger the length typically of the residuals. So you have a larger standard deviation of residuals. So let's take a look at a very specific example. This is an example we looked at a couple times of students' test scores as predicted by their attendance in school. So on the x-axis, we have the percent of school days they attended. And on the y-axis, we have their score on an Algebra 1 exam at the end of the year. So the standard deviation residuals for this relationship was 1.99, almost 2. We have to interpret this value. A good sentence stem to use when interpreting a standard deviation residuals is this. When using the least squares regression line with explanatory variable to predict response variable, will be typically off by about the value of S in units. So in this case, when using the least squares regression line, this model, with attendance, my explanatory variable, to predict test scores, my response variable, will typically be off by 1.99 points. That means the typical residual length, as we can see here, is about 2 test points. When we make a prediction, we'll typically be off by about 2 points in predicting that student's score, 2 points off above or below. So now we can think about, in terms of these bigger data sets, which predictor is the best predictor for how you're going to do in college in terms of your first year GPA. Well, what we can do is get all the residuals and we can see what is the standard deviation of these residuals for each of these predictors. And we can see here that we see some trends in these standard deviations. Specifically, the high school GPA model had the greatest prediction error. College GPA predictions were typically off by 0.563 points. So if we try and predict your college GPA with your high school GPA, we'll typically be off in that prediction by about 0.56 of a GPA point. Now, the SAT model made better predictions. Its prediction errors were typically lower at only 0.53 points. That was its standard deviation of residuals. So in this way, SAT is actually a stronger predictor of college GPA than high school GPA. Now, the best predictions, the least error, came from using both GPA and SAT together by using that composite score out of 100, combining those two things together. That was the lowest typical prediction error at 0.518. So let's return back to our key analysis. Why would colleges choose to require the SAT and the ACT again? Well, some colleges have found that the SAT provides a stronger signal of college success than if they just use high school GPA alone. But now you might be looking at these things and you're wondering, okay, there are some differences. I see the value using the SAT in terms of getting a strong relationship, but these numbers are all very close to each other. Is SAT really that much better than just using the high school GPA? Like, these numbers are really close. Why stress about the test? GPA does well enough, right? Because these numbers are so close. Well, in order to kind of evaluate that, we need to use another metric of strength in a correlation, which is the coefficient of determination, or R squared. So recall the correlation coefficient R. If you can see here, we have examples of different correlations of different directions and strengths, and here were the corresponding R values to those correlations. Now, if you take the correlation coefficient R and you square it, you get something called the coefficient of determination, R squared, which is a value between 0 and 1. It turns all negatives into a positive, and it's a measure of strength. Squaring the values gets rid of the negatives from R, and it emphasizes differences in strength. So let's see what I mean by that. So between the strong positive and the weak positive correlation, we see this difference in their correlation values. When we square those, we see an even bigger difference in the values. So by squaring the R values, we get a more sensitive measure of strength. The weak relationship has a very small R squared value compared to the strong relationship has a very high R squared value. So if you have an R squared value that's close to 0, it's generally considered a weak correlation. If R squared value close to 1 is generally considered a strong correlation. And the way you can interpret an R squared value is this. R squared percent of the variation in response variable can be explained by the linear relationship with the explanatory variable. Let's see what I mean by that. So here are two data sets. We're going to model each of them. And we can see here that the first data set is perfectly modeled by my line. The R squared value is 100%, 1.0. That's because the linear model completely explains the data's pattern. There is no error in this model. If I use the model to predict the data points, it would be a perfect prediction. There is no error. We have a completely explained model. So it's 100% of the variation Y is explained by this linear model with X. Now, in the second one, there is some errors, and that's going to happen with most data sets. And it means that I have a lower R squared. The linear model explains some of the data's pattern, but not all of it. It explains 72% of the variation in Y, but it can't explain all the variation. There are still some errors. There are still some residuals remaining. And so that's kind of the intuition behind R squared. So if we were to interpret the R squared for the relationship between high school GPA and first year college GPA at an R squared value of 0.13, that means we can plug it into this sentence stem. 13% of the variation in first year college GPA, my Y variable, is explained by the linear relationship with high school GPA, with my X variable. So high school GPA and the least square regression line model with it explains about 13% of the variation in first year college GPA. So it's not 0, but it's still not incredibly strong. And what we can do is we can get the R squared values for each of these relationships. So the R squared value for high school GPA, college GPA is 0.13. For the SAT, as the explanatory variable, is 0.22, higher. And then for using them both in the composite, that's the highest we have, 0.26. And you might be wondering, okay, well, are these really that different? Well, take a look at these values. So R squared 13% versus 26%, you put them in percentages. So including the SAT in that composite measure doubles the model prediction strength. We go from explaining 13% of the variation in college GPA to explaining 26% of the variation in college GPA. We have a pretty substantially stronger model. SAT substantially improves the model because we get a much stronger and more accurate predictions when we include it. That's shown by the R squared values. And finally, let's discuss the effect of outliers on these measures. So what's an outlier in a regression model? Well, let's look at our first model right here. Is that point way out there an outlier? Well, no. If you extend the least squares regression line, even though it's far away from the other points, it's still close to our linear model. So it's not an outlier. This one down here is an outlier. It is unusually far from the regression line compared to the other points. Let's take a look at this one. Is that unmarked point an outlier? Well, not really. Even though it is far from the least squares regression line, it's not unusually far relative to the other points. This is a very weak relationship. Most of the data is far from the regression line. So that point is not particularly unusually far, so it's not an outlier. So let's take a look at the effect of outliers on summary statistics. So here's a relationship with no outlier, and this is a strong negative correlation. And here's that same data set, but with an outlier included. Let's see what happens to the summary statistics. So the correlation goes from negative 0.94 to negative 0.61, so a decrease in magnitude. The R squared value went from 0.88 to 0.37, a big decrease in magnitude. And the standard deviation of the residuals went from 1.02 to 1.85. It increases because we have a higher typical residual value due to that outlier being the data set. So these three measures are not resistant to outliers. Outliers lower the strength of the relationship, which makes the R value smaller in magnitude, R squared value much smaller in magnitude, and the standard deviation of residuals larger in magnitude. All right, so let's get into our discussion question for today. So the UC report found that high school GPA used to be almost as strong as the SAT in predicting college GPA. Here's the 2007 cohort of applicants to UC schools. And you can see here it has an R-squared value of 0.2. It is a stronger predictor than the current high school GPA prediction value. So here's the old cohort with a R-squared value of 0.2 for its high school GPA predicting their college freshman GPA. And here's the modern cohort or the modern study where the R-squared value is only 0.13. It's a much weaker predictor of their first year college GPA to use their high school GPA. So our discussion question for today is, give one possible reason that you think high school GPA became a weaker prediction of college GPA over time. Why did that happen? And here's a hint, look at the shape of the data. Think about the shape of the data along the x-axis from the old cohort to the modern one. That's it for today's statisticians. We'll see you to discuss this in class.